Every second, 32 tires begin service worldwide. Each survives 100,000 miles of punishment, heat, friction, road impacts before replacement. Picture mountains of rubber growing daily. 2 billion tires manufactured annually, weighing 25 million tons combined. That's every car, truck, aircraft, and bicycle on Earth demanding fresh rubber constantly. How does liquid petroleum become indestructible black donuts? Why do old tires refuse to decompose for 500 years? Stick around. You'll discover the shocking chemical process transforming oil into immortal rubber and the jaw-dropping secret of where 85% of American worn tires end up. Hint? It's beneath your feet on football fields.
The story begins in Southeast Asian plantations, where rubber trees grow in geometric rows, stretching miles. Workers cut V-shaped grooves into bark, collecting milky latex sap in cups. Each tree produces 2 ounces daily, barely enough to fill shot glasses. Natural rubber comprises 30% of modern tires. The remainder uses synthetic alternatives derived from petroleum. Massive chemical plants crack crude oil into monomers, butadiene, styrene, then polymerize them into synthetic rubber matching natural properties. These facilities process 50,000 barrels daily, transforming black liquid into white crumb rubber. The similarity is uncanny. Petroleum-based rubber exhibits elasticity, strength, and durability rivaling million-year-old tree evolution. Chemistry replicates nature in months.
Next comes compounding, the secret sauce where rubber meets additives. Industrial mixers, standing 2 stories tall with rotors spinning at 80 RPM, blend rubber with carbon black, silica, sulfur, accelerators, and antioxidants. Carbon black, basically controlled soot production, reinforces rubber while providing characteristic black color. Without it, tires would be translucent white and fail within miles. Each tire compound contains 15 ingredients mixed in precise ratios. Tread rubber emphasizes durability. Sidewall rubber prioritizes flexibility. Inner liner uses butyl rubber for air retention. Formulations remain trade secrets. Michelin's compounds differ from Goodyear's, creating performance variations. Mixing takes 12 minutes at temperatures reaching 300 degrees Fahrenheit. The batch, weighing 500 pounds, emerges as uniform black mass ready for shaping. Giant extruders force hot rubber through dies, creating continuous strips of tread, sidewalls, and bead filler. These machines operate like industrial Play-Doh shapers, pushing material through shaped openings at forces exceeding 2,000 psi. Tread emerges with grooves pre-formed. Sidewalls arrive as smooth sheets. Cooling conveyors solidify the profiles. Meanwhile, calendaring machines squeeze rubber sheets to precise thickness, measured in thousands of inches, coating steel cord and fabric plies. These textile layers provide structural strength. Modern radial tires contain steel belts running at 0 degrees to rotation direction, fabric plies at 90 degrees, creating cross-brace architecture. Workers cut these components into precise lengths, stockpiling thousands of parts daily for assembly lines demanding continuous supply. Comes tire building, robotic ballet assembling 30 components into recognizable shapes. Cylindrical drums rotate while automated arms apply inner liner, body plies, steel belts, sidewalls, and tread in programmed sequence. Each component positions within 0.05-inch tolerance. Precision matters because imbalance at highway speeds creates dangerous vibrations. The green tire, uncured assembly, looks puffy and pale, lacking final tread pattern. Steel beads, wire bundles coated in rubber,
Anchor edges, providing mounting surfaces for wheel rims. These beads contain piano wire strength steel wound in continuous loops. Braking beads requires forces exceeding 5 tons, ensuring tires never separate from rims even during blowouts. Assembly takes 3 minutes per tire on modern automated lines, producing 2,000 tires daily.
Curing transforms green tires into finished products through heat, pressure, and chemistry. Massive presses, resembling medieval Iron Maidens, close around green tires. Internal bladders inflate with superheated steam at 350 degrees Fahrenheit and 200 psi. External mold segments, engraved with tread patterns, press inward simultaneously. This step is critical. Vulcanization. Sulfur atoms cross-link rubber polymer chains, creating three-dimensional molecular networks. Picture chain-link fences welded together at every intersection. That's vulcanized rubber at molecular level. The process, discovered accidentally by Charles Goodyear in 1839, transformed useless sticky material into engineering marvel. Curing takes 12 minutes. Afterward, tires emerge rigid with crisp tread patterns and permanent shape. They'll never soften or melt again. Vulcanization is irreversible.
After curing, quality control begins. X-ray machines scan internal structure, detecting steel belt misalignment, air pockets, or ply separations invisible externally. Uniformity machines spin tires at highway speeds, measuring force variations. Even 0.5-pound imbalance causes rejection. Ship tires must perform flawlessly at 120 miles per hour for tens of thousands of miles. Inspectors examine tread depth, sidewall finish, bead seating. DOT codes stamped into sidewalls identify manufacturing plant, date, batch number, critical for recalls. Modern tires undergo durability testing. Machines simulate 50,000 miles in 72 hours, cycling through temperature extremes, overloading, underinflation. Failure rate must stay below 0.1%. That's one defective tire per 1,000, because tire failure at highway speeds kills people.
Performance testing pushes limits beyond consumer use. Test drivers race prototype tires on proving grounds, executing emergency maneuvers, sustained high-speed runs, extreme weather conditions. Sensors measure temperatures, pressures, wear rates. Data feeds computer simulations refining compounds and construction. Winter tires use softer compounds, remaining flexible below freezing. Summer tires employ harder rubber, resisting heat degradation. All-season compromises performance for year-round versatility. Racing slicks sacrifice tread patterns for maximum contact area. Professional race tires last 200 miles but provide grip exceeding street tires tenfold. Tire engineering optimizes contradictory requirements: durability versus performance, comfort versus handling, cost versus longevity. Every design represents compromises, balancing physics against economics. This technology evolved from crude beginnings. Ancient Mesoamericans harvested rubber for balls and waterproofing 3,000 years ago, but material degraded rapidly. Charles Goodyear's 1839 vulcanization discovery changed everything. Accidentally dropping rubber sulfur mixture on hot stove created heat-stable material. The pneumatic tire emerged in 1888 when John Dunlop invented air-filled rubber tires for his son's tricycle. That innovation enabled automobile revolution. Cars needed shock absorption only inflatable rubber provided. Radial tire construction, invented by Michelin in 1946, improved durability 50% over bias ply designs. Today's run-flat tires, self-sealing compounds, and airless prototypes continue evolution. Annual global production exceeds 2 billion units, creating waste management crisis demanding solutions.
Carbon emissions drop by 62% using recycled tire crumb versus virgin rubber production. Industry saves over $41 billion annually through tire recycling. Processing old tires into crumb costs 70% less than manufacturing new rubber from petroleum. So here's the secret. 85% of American-worn tires avoid landfills through recycling programs. Shredders reduce tires to fingernail-sized crumb. This material becomes artificial turf infill, those black granules beneath football field grass that cushion impacts and improve drainage. Schools, parks, and stadiums nationwide walk on recycled tires daily without knowing. Crumb rubber also creates playground surfaces, running tracks, asphalt modifiers, improving road durability 20%. From petroleum to pavement to playing fields, cycle completes. Tires never die, they transform. That indestructible black donut refusing decomposition becomes humanity's accidental gift to circular economy. We've learned that immortal materials demand eternal responsibility.
Every second, factories worldwide produce carbon fiber threads 10 times stronger than steel, yet 5 times lighter. Picture this. A strand thinner than human hair supports weights exceeding 400 pounds, more than 2 adult humans hanging from a thread. Invisible at arm's length. These black filaments, woven into composites, form invisible to radar bombers, Formula One monocoques surviving 200-mile-per-hour crashes, and prosthetic limbs outperforming natural bone. How does ordinary plastic transform into material stronger than steel through fire? Why do engineers call carbon fiber the black aluminum, revolutionizing everything from spacecraft to tennis rackets? Stick around till the end. You'll discover the jaw-dropping reason carbon fiber doesn't break like metal but unravels like fabric, why recycling it became a technological arms race, and the shocking truth about what happens inside furnaces hotter than volcanic lava when atoms reorganize into crystalline perfection.
The story begins with polyacrylonitrile, pan fiber, the plastic precursor looking like white cotton thread. Massive spinning machines, standing 3 stories tall in climate-controlled facilities, extrude molten pan through spinnerets containing 50,000 microscopic holes. Each hole, measuring 3/10,000ths of an inch across, thinner than blood cells, produces one continuous filament. Picture spider silk production scaled to industrial extremes. These filaments emerge at speeds reaching 3,000 feet per minute, fast enough to cross football fields in seconds. Chemical baths stretch the fibers, aligning polymer chains parallel to fiber length. This molecular orientation determines everything. Randomly oriented polymers create weak thread. Aligned chains create strength rivaling steel. Workers monitor tension constantly. Variations of 2% cause inconsistent properties requiring entire batches, thousands of pounds worth, to be scrapped. The pan production facility operates 24/7, producing 50 tons daily, enough fiber to circle Earth's equator if laid end to end. Next comes oxidation, the first transformation where chemistry becomes alchemy. Massive ovens, stretching 200 feet long like horizontal tunnels, heat pan fibers to 500 degrees Fahrenheit in pure oxygen atmosphere. Inside these furnaces, oxygen atoms attack carbon-hydrogen bonds in the polymer backbone. Hydrogen burns away as water vapor, leaving behind carbon-nitrogen ladder structures stabilized through cross-linking. This stabilization process takes 90 minutes as fibers crawl through ovens on tensioned rollers. Temperature control matters critically. Too hot, fibers ignite catastrophically. Too cold, cross-linking remains incomplete, causing failure during subsequent heating. The oxidation chamber maintains oxygen concentration at 23% with tolerance of 0.5%. Operators monitor fiber color constantly, watching white pan transform through yellow to dark brown. That color change represents chemical metamorphosis, polymer becoming something fundamentally different, no longer meltable, now heat-resistant enough to survive temperatures that vaporize aluminum.
Giant carbonization furnaces, operating at temperatures exceeding 3,000 degrees Fahrenheit, complete the transformation. These aren't ordinary ovens, they're inert atmosphere chambers purged with nitrogen gas, creating environments where oxygen molecules cannot exist. Inside this oxygen-free inferno, stabilized fibers lose nitrogen, hydrogen, and other non-carbon elements through thermal decomposition. Only carbon remains, reorganizing into graphite-like crystalline structures. The process occurs in stages. First, furnaces heat fibers to 2,700 degrees, driving off 90% of non-carbon atoms. The fiber shrinks 25%, density increasing as material compacts. Second stage furnaces push temperatures to 4,000 degrees for graphitization, the process aligning carbon atoms into perfect hexagonal sheets stacked like microscopic playing cards. This crystalline perfection gives carbon fiber its extraordinary properties. Processing takes 3 hours, crawling through furnace sections totaling 1,000 feet long. One power interruption, one oxygen leak, and fibers oxidize catastrophically, burning like magnesium flares, destroying millions in equipment. Now comes surface treatment, electrolytic oxidation creating reactive sites for resin bonding. The carbon fiber, now black as obsidian and measuring just 0.003 inches diameter, passes through electrolyte baths while electric current flows through it. This electrochemical attack roughens the fiber surface at nanometer scale, creating anchor points where epoxy resins chemically bond. Picture this. Untreated carbon fiber in epoxy resin slides apart like oiled rope, strong individually but weak as composite. Surface-treated fiber bonds molecularly to resin, creating integrated structure where fiber and matrix function as single material. Modern aerospace composites achieve interface strengths exceeding 12,000 pounds per square inch, meaning the bond between fiber and resin is stronger than many metals themselves. This step is critical because composite strength depends not just on fiber properties, but on load transfer efficiency from matrix to fiber. Poor surface treatment causes delamination, layers separating under stress, the characteristic failure mode making carbon composites unravel rather than fracture. The sizing application follows, coating fibers with protective polymer layer. Massive rollers submerge fiber tows, bundles containing 12,000 individual filaments through sizing baths containing proprietary polymer formulations. This coating serves triple purpose: protects fibers during handling, improves resin wetting during composite layup, and provides limited abrasion resistance. Workers wind treated fiber onto spools holding 10 miles of continuous filament. These spools, weighing 200 pounds each, ship to composite manufacturers worldwide. Quality control inspects random samples continuously. Tensile testing machines pull individual fibers until failure, measuring breaking strength, elastic modulus, and elongation. Modern aerospace-grade carbon fiber withstands stresses exceeding 800,000 pounds per square inch, 50 times stronger than structural steel. The fiber stretches only 1.5% before breaking. Steel deforms 300% more. That limited elongation explains why carbon structures crack suddenly rather than bending. No warning, just instantaneous failure when stress exceeds capacity.
After arriving at composite manufacturers, fibers get woven into fabrics or used as unidirectional tapes. Automated looms, programmed like textile machines but operating at glacial speeds to prevent fiber damage, weave intricate patterns. Plain weave creates checkerboard appearance, twill weave produces diagonal patterns, satin weave maximizes smoothness for aerodynamic surfaces. Each weave pattern offers different mechanical properties. Engineers select patterns matching stress directions. Picture this. Laying up carbon composite resembles origami, with materials costing $300 per pound. Technicians cut fabric patterns, stacking layers in precise orientations. Each ply orientation, 0 degrees, 45 degrees, 90 degrees, contributes specific strength characteristics. A typical aerospace laminate contains 40 plies, each 0.005 inches thick, creating structures 8 inches thick, yet lighter than equivalent aluminum.
Between each ply, workers brush epoxy resin, ensuring complete fiber wetting. Air bubbles trapped between layers become stress concentrators, causing catastrophic failure. So layup occurs in clean rooms, maintaining air purity rivaling semiconductor fabs.
Curing transforms wet layup into solid composite through heat and pressure. Massive autoclaves, pressure vessels 30 feet in diameter and 100 feet long, create environments combining 300 degrees Fahrenheit and 100 psi pressure. Inside these industrial pressure cookers, epoxy resin chemically cross-links while pressure squeezes out excess resin and air voids, compacting layers into dense laminates. The cure cycle takes 8 hours following computer-controlled temperature and pressure ramps. Heat too fast, resin boils, creating voids. Heat too slow, productivity plummets. Modern autoclaves monitor 200 sensors simultaneously, adjusting conditions to within 1 degree and 0.5 psi. After curing, parts exit as rigid structures, material properties now locked permanently. Non-destructive testing using ultrasound and X-rays searches for defects. Even microscopic voids or delaminations require part rejection because carbon composites tolerate 0 defects. Unlike metals tolerating small cracks through ductility, carbon composites fail catastrophically once cracks initiate. That brittleness demands perfection during manufacturing.
This technology emerged from 1960 space race. Thomas Edison experimented with carbon filaments in 1880s for light bulbs. But modern carbon fiber originated when British researcher William Watt developed pan-based process in 1963 at Royal Aircraft Establishment. The breakthrough enabled high-strength fibers commercially viable. Formula One adopted carbon fiber in 1981 when McLaren built the first composite monocoque chassis. Driver John Watson walked away from a 200-mile-per-hour crash at Monza, the carbon tub protecting him despite complete car disintegration. That demonstration convinced aerospace industry. Boeing's 787 Dreamliner, entering service in 2011, uses 50% composite materials by weight. Wings, fuselage sections, tail, slashing fuel consumption 20% versus aluminum equivalents. The B-2 Spirit stealth bomber, revealed in 1989, incorporates carbon composites extensively. The radar-transparent properties, combined with geometric shaping, create aircraft virtually invisible to detection. Today, carbon fiber production exceeds 120,000 tons annually, growing 15% yearly as industries discover applications from wind turbine blades to bicycle frames. Carbon emissions drop by 32% when using carbon fiber in aircraft versus aluminum. Lighter structures require less fuel over millions of flight miles. Industry saves over $68 billion annually through weight reduction in transportation. Wind turbines using carbon fiber blades generate 18% more electricity through longer, lighter blades, impossible with fiberglass. So here's the secret promise. Carbon fiber doesn't break, it delaminates. Unlike metal fracturing through crack propagation, carbon composites fail through layer separation. Impact damage creates barely visible surface dimples, hiding extensive internal delamination, while composites require ultrasonic inspection after any impact. That failure mode makes recycling challenging. You can't melt carbon fiber like aluminum. Heating destroys the crystalline structure that provides strength. Current recycling uses pyrolysis, heating composites to 1,000 degrees in oxygen-free environments, burning away resin while preserving fibers. Recovered fibers retain 70% of original strength, creating secondary markets. From plastic thread to aerospace revolution, cycle completes. Carbon fiber represents humanity's ability to reorganize matter at atomic level, creating materials nature never intended. We've learned to cook polymers in furnaces hotter than volcanoes, aligning carbon atoms into crystalline perfection, stronger than any metal, yet lighter than water. That thread, thinner than hair, doesn't just reduce weight. It enables impossible structures. aircraft wings spanning 200 feet without internal support, prosthetics stronger than bone, spacecraft components surviving forces that pulverize steel. We've engineered the future, one microscopic fiber at a time. The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the Bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains.
The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor.
At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke.
This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use, but its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousandths of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton.
The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746. But mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they served for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level. How one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car, yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.08 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousands of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade,
Every atom from root to tip belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a three-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a three-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%.
Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, yttria-stabilized zirconia ceramic applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60-to-1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards but runs ice cold compared to the 3,000-degree combustion gases outside.
Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2000 degrees. Hot enough to glow orange, but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself.